Hello everyone, this is dynamic programming. So what is dynamic programming? Dynamic programming is where you break down the problem into smaller and smaller subproblems. Then these subproblems are solved in a way, and only once, so you don't repeat solving them, and stored, so the results can be reused to solve more subproblems. These subproblems can then be used to solve the problem. For example, you can sum them, you can take the maximum, the minimum, make some function to solve the problem, etc. So there are two types of dynamic programming: bottom-up or tabulation and top-down or memorization. So what is bottom-up or tabulation? Bottom-up or tabulation is basically where you start at a starting point in a graph, vector, table, etc. and you calculate the subproblems in a specific order to store the answers to these subproblems. These answers will help solve future subproblems and so on until they can be used to solve the actual problem. Top-down or memorization. So in normal recursion, you'll see what you want to calculate or find at the end, and then calculate the things you need for that, as well as the things you need for the things that you need for it, and so on and so on. And unfortunately, this creates a lot of repetition, and we calculate many of the things that we already calculated before, and this ultimately leads to an exponential time complexity. This is really bad because this increases the time taken for the code to run. To solve this, we can use memorization. Instead of recomputing the same values over and over again, we store them in memory. So if we have already calculated it, we just retrieve the result whenever we need it. This reduces the time complexity. Example would be the SAPO Round 2 Question 3 2020 this year. This question basically said we have to count the number of ways to go from the top left block to the bottom right block of a grid, only moving down or right. And we cannot pass through these block cells marked with an X in the diagram on the right. So that's just an example. So first thing to notice is how every cell is just the sum of the numbers of the cells above and to the left. So for example, that 2 is just the number above it, the 1, and the number left to it, 1 added together. 1 plus 1 is 2. Knowing this, what we can do to solve the problem is first fill in the first row with 1s, unless one of the things are blocked, in which case you just fill in everything after that with 0, because after something's blocked, we can't go back up to fill in the first row. And then for every row after that, we work on each cell from left to right in each row. So we go row by row from left to right by summing the number in the cell above and to the left of it. And finally, when you get to the last row, at the end, we can calculate the bottom right cell by adding the one above it and the one left of it. And the problem is done. This was my code for the problem. The code just says, I just initiate variables nm by the inputs. I make a grid. I fill in the first row with all 1s, unless there is a there's like a blocked grid, blocked cell, in which case I just make everything else 0. I do the same for the first column, and then for every block after it, I just add the sum of the cell above and to the left of it. And the time complexity of this code is O(n)m. And this was an example of bottom-up or tabulation, as we started at a point, the upper left cell, and we calculated values in an order, so row by row, until we got to the end, the bottom right cell. If, for example, we wanted to solve this question using top-down or memorization, we would first need to look at how we'd solve this problem using recursion. We need to start at the end, the right bottom cell, and see which cells we have to add to get that cell. And then we see which cells we have to add to get those cells, and so on. So we look at what we want, the bottom right cell. We look at what we have to add to get the cell above it, since the cell left of it is blocked. And then for that cell, we add the top and the left. And then again, above and left. And for the other one, above and left. Now you'll notice that one of the cells has already been calculated more than once, this cell. And as the grid gets larger, the amount of repetitions of calculations will go exponentially. This is really bad as it increases the time complexity of the code and it just makes the code run slower and it takes longer for the code to run. How do we fix this? Well, we can use memorization to store the things we have already calculated in a list or somewhere in memory so we can just retrieve the results when needed instead of recalculating the same thing many times. So that answer to that cell is stored in memory and whenever we need it, we can just retrieve it from the memory. So when is it best to use which one? Bottom-up or tabulation or top-down memorization? So for bottom-up, we use this method when there's an obvious and a nice order in which you can calculate the subproblems in such a way that you always have everything you need already calculated for calculating next or future subproblems. So basically, we need to find an order in which every time we try to calculate a subproblem, we have already calculated everything we need for calculating that subproblem. Like in this question that we did, the SAP round 2 question 3, we can just do it row by row and we're guaranteed that for every subproblem, so for every cell's value we want, we already calculated the cell above and to the left of it. So we usually use bottom-up tabulation when there's a nice order because it is faster to code and it runs faster as recursion or memorization has a lot of recursive calls and return statements, and it usually outperforms memorization by a constant factor. So top-down or memorization. Sometimes there isn't a nice way to see where to begin and end a problem, or the order in which you do it is not that clear. This is when memorization is more useful. Instead of trying to come up with a complicated order in which to evaluate the subproblems, we can just try to see the end and work backwards. This works because, first of all, we don't know an order in which we can calculate the subproblem such that the predecessors have already been evaluated to be used to calculate the current subproblem. So top-down or memorization would be better. We use memorization in things like a directed acyclic graph that has not been topologically sorted to give an order for the bottom-up or tabulation. Working backwards is easier as we do not have to follow an order, it just finds all the values. We also know that this process is finite as it is acyclic, so there are no cycles, it doesn't just go around in circles infinitely, so the process terminates. An example problem would be the coin problem. So let's consider a problem where we're given a set of coins and our task is to form a sum of money, n, using the coins. The values of the coins are coins C1 all the way to Cn, and each coin can be used infinitely many times. What is the minimum number of coins needed for n? We could first try something like recursion. A recursion code for this would look something like this. This is C++. Basically, if the money is less than 0, return infinity, as you can't make negative money with coins. And if the money is 0, then return 0 because we don't need any coins to make $0 or 0 and whatever. And for every money, if it's a positive number, then we just for all our coins, we just work out the one that's before it. So basically, say our coins are 1, 2, and 3, and you have to try to calculate 8. Then calculating 8 would be the same as taking the coin of value 1 out and calculating the minimum number of coins needed for 7, and then adding that 1 coin back. So we just repeat that for all the coins possible and for all until it gets to 0. Unfortunately, recursion, just like in the SAP round 2 question 3 problem, the grid walk problem, it repeats a lot of calculations for the same thing. And so we use arrays to store the information. The array ready tells the program whether the calculation has already been solved, and the array value tells us what the value of the calculation is. So a program using memorization would look something like this. So we store the information in the value and ready, so the value stores value and the ready stores whether we already calculated it. And yeah, this time complexity is O and M. So constructing a solution, so sometimes we are asked to both find the value of an optimal solution and to give an example of how such a solution can be constructed. In our examples in the previous slides, in the codes, they only tell us what the optimal solution is. But using GP, we can also get the actual coins that make up the optimal solution. So we can use an additional array to store the first coin in every solution. So say the solution for 8 is 1, 2, and 5, then we just store 1. We can then just change the code so it actually stores the first coins in the array. And then what we do is we just add a few lines. We just calculate the coins, the optimal solution, by adding a few lines of additional code. And we keep getting the first coin and remove that amount of the first coin and repeat. So say we want to calculate the coins to calculate $8. And say for $8, the first coin in that's the minimum solution is 2. Then we take the 2 out and we see what the first coin for 6 is, and for whatever it is, until it gets to 0. And all those first coins will make up the original problem we want. And that is all. Thank you.